All right, first thing I'll talk about today is Newton's law of universal gravitation, or as I will refer to it as NLUG. And there are three parts to this particular law. So not only do we have Newton's three laws of general motion that we've talked about, it also has this law of gravitation, and it's universal gravitation because it works throughout the universe. Okay? So the three parts. First part is pretty self-explanatory. It says every particle in the universe attracts every other particle through the force of gravity. Now, what does this mean exactly for you? If you have mass, you are technically attracted to every other object that has mass. So yes, you are attracted to the desk that you sit in. You are attracted to the house that you live in. You're attracted to your parents. Gross. Ew. You're attracted to everybody you sit next to on a daily basis. When you walk by somebody in the hall, you are technically gravitationally attracted to them. However, it's a very small gravitational force because you, technically, no matter how big of a person you are, have a small mass in relationship to, say, planets, which are quite large. Okay, so you are much more gravitationally bound to the planet than you would be to other objects. Another thing, number 2 says f of g is proportional to the product of your masses. So one thing I'd like to write here is f of g is proportional to the product of the masses. And that means, okay, if I multiply the two masses together, that's going to affect the f of g. And they're directly proportional. So if the masses go up, then so should f of g. So the bigger the object, the bigger gravitational attraction it should have. Like, for instance, the sun is fairly large. We are gravitationally bound to that. We're gravitationally bound to the sun a heck of a lot more than we're gravitationally bound to, say, the moon, even though we are technically also gravitationally bound to that as well. Okay. The third one, f of g is inversely proportional to the square of the distance between their centers. Okay. Now, this is a little tricky. Inversely proportional. So f of g is proportional to 1 over the square of the distance between them. Now, what I like to do is think about this. If I've got one object here and another object over here, and this object is, say, circling, then the distance between here and here is really the radius. Okay? If I extended that circle all the way around or whatnot. Okay? So this is really 1 over r squared. Okay? So these are the three parts. So we have another equation for f of g. Okay? Where f of g is directly proportional to the product of the masses and inversely proportional to the distance between them squared. Now, there is also another thing in here, and it's big capital G. Okay? And what this is this is called the universal constant, where G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. And now, this unit makes sense, because if I've got meters squared on the top, that takes care of the radius, which is in meters squared on the bottom. And then there's mass times mass on the top, so the kilograms on the bottom will cancel that, and you're left with newtons, which is a unit of force. Now, this particular value came about experimentally by Henry Cavendish. He was the original one who kind of came up with that value. Newton realized the relationships. Cavendish came up with that number. Okay. So let's talk about a couple examples here. If I were to double one of the masses, if just one mass went up, if this went from 1m to 2m, then f of g would double. But if I double both masses, remember that f of g is proportional to the product of their masses. So if this was originally 1 and 1, and now it's 2 and 2, then the force of gravity goes up by a factor of 4. Okay? Distance is a bit trickier. Okay? If I double the distance, or the radius between the objects, not only is it going from 1 to 2, but then I'm also squaring it. So if it was originally 1 squared, now it's 2 squared. So that would put a 4 on the bottom. That would cut the force down to a quarter of what you originally had. And then if I say tripled the radius, okay, well now 3 squared would be 9, and we would get a ninth of the original. And if I made it 10 times bigger, then 10 squared would be 100 on the bottom, and we'd have 100th of the original force. So the distance between objects greatly decreases that gravitational force. Okay, so I want to go over just a couple little helpful hints for you when you get to some of your homework. We know from past units that f of g is mg. We now know that f of g, I should capitalize this, is g m1 m2 over r squared. Okay, now remember that f of g was calculated for the object. So one of these masses represents this object. So I'm just going to call this mass 1. Okay. Well, if these two things are equal, then I can set mg equal to g m1 m2 over r squared. Okay. And if we look at some stuff that we can do with this, we can cancel out the masses, and we're left with g is big G times m2 over r squared. Now, if you were, say, to plug in the mass of the Earth and the radius of the Earth, guess what you would get for g, little g, that is. You would get 9.8, which is the value of gravity on this planet. Okay, that's pretty much how they calculated that particular value. Okay. Now, one other little extension from this, and this is a lot for both AP and IB here, but this G value is not always written as this. And again, we can kind of go back to this particular equation, but there's another thing that might come up, and it's called gravitational field strength, where they record G in terms of the force over the mass. Okay. This will often be called just gravitational field strength. Oops. And the thing that I want you to make note of is if they're referring to gravitational field strength, they will often refer to G in terms of newtons per kilogram. So they're describing gravitational field as a force per unit mass. How much force is acting on a particular mass, as opposed to reducing this down to an acceleration, like meters per second squared. Okay. One other thing that is important to remember, in a lot of the problems where you're dealing with this r, okay, the radius can be a bit tricky. Okay. If we were to talk about an object, like let's just say this is the Earth here, okay, and there's a satellite, which I know a couple of you will tell me looks like a TIE fighter from Star Wars, and that's because I'm that good of a drawer. Technically, if this is the center of the planet, you have the radius of the planet plus the orbital height. This needs to be the r value in any of your equations. Okay, so don't forget that not only do you have to know the radius of the planet, you also have to know the orbital height. Now, I'm going to give you some values that might be helpful for some problems, and you can look these up if they weren't available for you or if I wasn't giving them to you. But you might need in some of your problems the mass of the Sun, which is 1.99 times 10 to the 30th. Mass of the Moon, 7.35 times 10 to the 22nd kilograms. You might need the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. And you might need, say, the radius of the Earth, which is 6.38 times 10 to the 6th meters. Okay. Also be very careful in this particular unit, especially if you're looking at this value. If you're going to be using universal law of gravitation, you need to have all your distances in meters and all your masses in kilograms. Okay. Now this one is the tricky one because astronomical distances are most oftentimes given in at least kilometers, if not even a larger unit. But just be careful of that. Okay. All right, that's it for n lug.